Okay, let's just wait for a couple of minutes, 2, 3 minutes after that I will start. So let me start now. Uh, in the last problem solving session, I have mostly discussed about uh, some basic concepts of the probability, like the PDF, CDF, what are those? Then we have seen about the concept of estimators, different distributions like which are useful here, like normal distribution, t distributions, all those, and how we can create those t distribution from the normal 0, 1, because it is mostly used in the hypothesis testing and all. And we have solved one question where we have seen that how to test the hypothesis. Today also we will do one of the problems because the first two assignments are mostly based on those concepts and basics of the like expectation values, variance, how you solve it based on that. So today also we will take up one problem and with revising those concepts which we have done in the last class. Along with that, today's new concepts which have been covered in the week 2 in the simple linear regression that we will do and we will apply in this particular question which I will write. Now, once that is over, I will maybe if time is there, then we can go ahead with some multi-linear regressions, some basic equations. Uh, Mostly, I will cover the multilinear regression with a problem in the next class. Just a minute. Yeah. Okay. So let us start with it. So first, I will start with only one question because I will apply all those concepts in this particular question. So the question is something like this. This is given X and Y, the data sets are given. In the assignment questions, I have seen that it might not be that this X and Y, all the data set points are given. They will give you some summation X square, summation X or X bar. So you have to, based on that, you have to just calculate. So you don't need to worry about this X and Y. And sometimes there may be some relations which will be helpful that can lead to calculation of beta 1 or beta 2, beta naught. Okay, so in general, the questions are something like that. That 5, suppose this is some x, which is in our control, means we can vary it. Whereas y is not in our control. Whatever the experiment outcome is, it will come in the y. So y is a random variable, which we have discussed in the earlier class. So this is a random variable, whereas this is not. This is some kind of a, when we will use the summations and all those things, this is mostly termed as a constant kind of a quantity, x bar, everything. Okay. So this is 5, 7, then 12, 16, then 20, and the y, the sample comes out to be 40, 120, 180, 210, and 240. Okay, so this is the question uh, where we will be using different concepts of simple linear regression, whatever we have learned in the week one. Also, you have seen in the what you call as your week one lecture. Uh, Along with that, the problem solving sessions which people might be attending. So based on that, we will try to see this. Okay, and along with that, we will also solve some new concepts which have been covered in the week two. So we will also do that. Okay, so this is the question, but this is not the question, but it is the data set which is given x and y. Now the question comes is that uh, so the first problem is that find the what you call as the estimated slope and intercept. And this is the simple thing because this is the starting point where you will do the linear regression model, simple linear regression model. So find the estimated slope and intercept. Why estimated? Because we don't know the population slope and the population, what you call as the population intercept. We don't know that. What we know is this sample, the sample points which have been given to us. We don't know the actual distribution of y, what is its population parameter. We don't know those. So we have to estimate something. Okay, estimate what? Estimate the population parameter, like the intercept and the slope of the population. We will be estimating it. Okay, so that's why it is the estimated slope and intercept. Whenever we calculate the slope and intercept in the linear regression based on this data set given in any question anywhere, that is nothing but the estimated, not the real. Okay. So, so we will start with this that find the estimated slope and the intercept. So, what is the y hat or y cap, whatever you wanted to say? So, beta naught cap plus beta 1 cap x. So, this is the estimated or estimated line or the fitted linear regression line. Okay, this is the linear regression uh, estimated linear regression model. Okay. Actual is y is equal to beta naught x plus, sorry, y is equal to beta naught plus beta 1 x plus x side naught. Some error term is there. But when you are estimating, it comes out something like this, where beta naught cap and beta 1 hat, or these are the estimators of the slope and the intercept. Fine. So to calculate that, what we require, we know that beta 1 cap or beta 1 hat, whatever you wanted to say. So this is nothing but xi minus h bar, yi minus y bar divided by summation xi minus x bar whole square. And what is beta naught hat? That is equal to beta 1 bar, sorry, not beta 1 bar, that is y bar minus beta 1 hat x bar. This is what through which we can calculate the beta naught and the beta 1. Okay, so I can just switch off the camera because I keep on the close. Yeah. Okay, so now this is the main. uh, formula for doing this. Now there is another formula for beta 1 based on only the summation, not bars. This x bar and y bar will not come. I have showed you in the last class also that this can be written in another form. So both are similar. Okay. So beta 1 hat can also be written as n summation xy minus summation x summation y divided by n summation x square minus summation x whole square. Okay, all summations are here also and here also. All summations are from I is equal to 1 to n. Here n is how much? 1, 2, 3, 4, 5. So there are 5 samples. So n is equal to 5. Okay, so you can use any of them. Based on that, whichever you wanted to use, you just calculate. Okay, fine. So we will use in this case this one and this. These are the two definitions of beta 1 and beta naught hat. We will be using this. So for that, let us again write whatever the thing is and calculate some more things. Okay, because this is xi, this is yi, this is given to us. I will write it. We need xi minus x bar. Okay, we need yi minus y bar, and we need xi minus x bar into yi minus y bar. This is the multiplication which we need. And finally, we need xi minus x bar whole square. Okay. So just a minute, I can erase and start from this side. So you have, okay, this is xi, this is yi, this is xi minus x bar, this is yi minus y bar, this is xi minus x bar into yi minus y bar, and finally you have xi minus x bar whole square. That's all. Okay. So what are the xi values which are given in the data? This is 5, 7, 12, 16, and 20. What about the YIs? 40, 120, 180, 210, and 240. Okay. So let us first find out this X bar. Okay. This X bar, Y bar, these are easy to find. Let us find out that. Okay. So what is the XI bar or X bar? Just sum it up and divide it by 5. Okay, so n is equal to 5. We know it. Okay, so what is x bar? So it is 20 plus 16 plus 12 plus 7 plus 5. It comes out to be about, uh, this x bar comes out to be about 12. Okay, so you can check it with the mathematical calculation. Okay. Similarly, this y bar is nothing but summation all these y divided by 5, means divided by n. The stupid mean you have to do. Okay. So based on my calculation, y bar comes out to be about 158. Okay. So x bar is 12, y bar is 58. We have found out this x bar and y bar. Now what we have to do? We have to calculate xi minus x bar and yi minus y bar. So let's do it. Xi minus x bar. So it is nothing but 5 minus 12, which is nothing but minus 7. Then 7 minus 12, which is nothing but minus 5. 12 minus 12 is 0. Then 16 minus 12 is 4. 20 minus 12 is 8. Right? So these are the xi minus x bar values. What about yi minus y bar values? So it is 40 minus, I'm not writing it, 40 minus 158 because this is 40 and y bar is 158. So 40 minus 158 is minus 118. Okay. Next 120 minus 158. What is that? About minus 38. 180 minus 158 greater. So it becomes 22. 210 minus 158. So how much it will be? 40, 50, 52. Right? And what about the last one? 240 minus 158. So it comes out to be 40, 40, 80 and 2, 82. So these are the deviations from the mean. We call this term in the statistics yi minus y bar as a deviation. Deviation of what? Deviation of y, all the y's from the mean value. Very popularly, it is also called as anomalies. Okay, uh, X anomalies, Y anomalies we have calculated. Or you can call this as the deviation from the mean value. Right. So we have calculated xi minus x bar and yi minus y bar. Now, in the equation, if you look at, it is summation of xi minus x bar multiplied by y minus y. So we have to multiply it, xi minus x bar into y minus y bar, and then sum it. Okay. So let us do that. So minus 118 into minus 7. So let us write minus 7 into minus 118. That comes out to be about, I have calculated already. So it is 826. Okay. Then it is minus 5 into minus 38. That comes out to be about 190. Next, 0 into 22. Easy, 0. Next, it is 4 into 52. It comes out to be 208. And the last, which is 8 into 82. How much it is? About 656. Right? So the numerator term, that is summation xi minus x bar, yi minus y bar, this is already done. Now what we have to do is that you have to sum all this. You have to sum all this. That's all. Okay. And in the denominator, you find xi minus x bar whole square. So already my xi minus x bar is calculated. So these are already calculated. Now we have to square it each and every values. Okay. So it is nothing but minus 7 square. What is that? 49. Minus 5 square is 25. 0 square is 0. 4 square is 16. 8 square, oh sorry, just a minute. This is 0. 4 square is 16. 8 square is 64. That's all. So xi minus x bar whole square is also calculated. Now everything is done. We need to sum this and sum this. That's all. And then we divide. That's the answer. Okay. So now let me again write it. So beta 1 cap is nothing but xi minus x bar into yi minus y bar divided by summation of xi minus x bar whole square. Correct? This is done. So we need to calculate this. So what is summation of xi minus x bar into yi minus y bar? Yeah, yi minus y bar. What is this? So you have to add all these. So what is that? 826 plus 190 plus 0 plus 208 plus 656. Right? So how much it is? So if you calculate out, it will come out to be about 1880. Let me check it once using calculator. So 826 plus 190 plus 208 plus 656. And that comes out to be 1880. Right. So this is the numerator part. What about the denominator? Denominator is denominator is xi minus x bar whole square. Right. So that is also being done. So it's 49 plus 25 plus 15 plus 64. 49 plus 25 plus 0 plus 60 plus 64. So 64 and 16 is 80. 80 plus 25, 105. 105 and 49. So it's 114, 24, 34, 44, 54. About 154. So this is your xi minus x bar whole square. Right. So done. Beta 1 is already done. You can calculate now. So beta 1 hat is 1880. The summation of xi minus x bar into yi minus y bar in the numerator. And in the denominator, you have 154. Right. So if you do this division, it comes out to be about 12.208. You can approximate it to two places of decimal, it becomes 21. So 12.21 is the estimated slope. So this is the estimated slope, right? So this is the estimated slope which we have already calculated. What about beta naught, the estimated intercept? It is given as y bar minus beta 1 hat x bar. Okay, so what is y bar? We have already calculated, that is I think 158. 158 we have already calculated here, right? So this is 158 minus beta 1 I already calculated 12.21 into x bar. Now what is x bar? 12. So if you now do this calculation, let me do it once. So it is 12.21 into 12 and 158 minus 12. So it is about 11.48. You can keep it like that because we have already kept it the beta 1 right in up to two places of decimal. Let us keep it. Let us not write it 11.5. Okay. So this now becomes the estimated intercept, right? Intercept. So now my estimated regression line becomes y hat is equal to beta naught hat plus beta 1 hat x. Right. So what is beta naught hat? Is 11.48. We have calculated. Beta 1 hat 12.21 into x. So this is your y hat. Right. So this is now my new estimated line, straight line, or the fitted line. What you say? Okay. What you say? So this is estimated fitted line or fitted data, predicted data, whatever you want to say. Fitted data. Okay. So there are several observations. Just just approximately I'm just drawing. So it's something like this. Okay, some positive slope about 12.21 and the intercept here is 11.48 and this is the y hat. Okay. So this is x, this is y. This is somehow it looks like. Okay, so we have already calculated the estimated slope and the intercept. The first problem is done, right? Now the next is about the hypothesis testing. We have also seen in the last problem solving session, which I have taken. There we have seen the hypothesis testing using key statistic, key test. We do the hypothesis. So let us do that. Let us do that again. So that will be a quick revision. So now the next problem, second, is let us test the hypothesis. So test hypothesis at 5% significance level. Okay, so what are the hypotheses? This is the null hypothesis is that we generally take this as the null hypothesis that the population slope is equal to 0. And H1 is that the population slope is not equal to 0. Whenever in the hypothesis testing, you might be knowing, you all might be knowing that beta 1 is not equal to 0 means that it is not one-sided, it's a two-sided. It can be either positive, it can be either negative. We don't know. Okay, so it's a two-sided thing. So it can be here also and here also. Both this area, so this becomes your alpha by 2, this becomes your alpha by 2. Alpha by 2 is the area under the curve, this shaded curve. Okay, this both alpha by 2 plus alpha by 2, this gives you alpha. And this alpha is this, okay, which is 5% means 5 by 100, 0.05. This alpha is 0.05, so this has to be 0.025 and 0.025. So just remember, in case you might be knowing that whenever this not equal to 0, whether it is a regression process or any process in the statistics, wherever it is not equal to 0, any null hypothesis comes, you have to take a two-sided distribution. But if it is that greater than 0 or less than 0, you have to take one-sided distribution. That's all. Okay, fine. So this is now done. Now to do this hypothesis testing, we already know some basics. So let us start. Right? Yeah. So we start with the fact that beta hat, the estimated slope, is the normal distribution of beta and sigma square by Sx. What is Sx? What we have calculated here. So what is this? This is okay. Okay. This xi minus x bar whole square summation is the Sx. Right. Okay. Can you just uh, turn your mic off? Okay, I've done. Fine. So this is your uh, beta hat. Generally, we take this kind of a distribution. This is normal distribution. Okay, so if this is true, then can we write beta hat minus beta divided by root over sigma square by sxx as normal 0 1? This we have seen. This we have discussed in details in the last class, where we have seen that whenever one random variable is a linear function of another random variable, then both the random variables have the same distribution. So if one of the distribution is known, then the other one will be also known. Okay. So this is also you can see that this is nothing but a linear function of beta cap and beta. So beta, if it is a normal distribution, then beta cap is also a normal distribution. Right. So this is the thing. Means beta cap is, if it is a normal distribution, then this parameter will also be a normal distribution, but with a mean of this means you have to take the expectation value of this and variance of it. Okay, so this is done. This is already known, I assume. Okay, here sigma square, the population variance. Sigma square is the population variance. Population variance is unknown. I don't know the population variance. We only have samples. We don't know the population. Okay, so population variance is unknown. Right. So population variance is unknown. So if the population variance is unknown, we generally take an estimated for this variance, which is nothing but MS residual. And this MS residual is SS residual divided by the degrees of freedom of SS residual, that is n minus 2. Okay. So this is what we generally take. What is this SS residual? Is summation of EI square. Okay. What is this EI square? Let us just quickly do it. Yi minus y hat I whole square. I is equal to 1 to n. This is your residual sum of square. Okay. So SS residual. And why degrees of freedom is n minus 2? There are n observations, but two constants because summation EI is always 0 and summation XI is also 0. These are the two constants because of which 2 degrees of freedom is lost. So out of n, now you have lost two uh, independent terms. So you have n minus 2 degrees of freedom. Fine, this is already discussed. So we will just quickly replace. Yeah, tell me. Right, right, right. So what happens is that you have n samples, right? Here you have n samples. Like here in case it is 5 samples are there. But what happens is that, see, this is yi minus y hat whole square, right? This is your ei square. But if this SS residual, if you look at degrees of freedom, it comes out to be n minus 2 instead of n. But this y, see, this SS residual is nothing but I is equal to 1 to n yi minus yi hat whole square, right? So you have n summation. So you have n degrees of freedom, n independent uh, terms you have to calculate. Okay, so this time y1, y2, y3, these are all independent samples. When you do some experiments independently, you get this y1, this y2, this y3. These are all independent and comes from different distribution, independent distribution. Okay, right? Yeah. So then it should be having n degrees of freedom, but these are the two constants. Why these two constants? Because ei is what? Yi minus yi hat. This is equal to 0. So this actually cuts off one of the degrees of freedom. That is the independent, what you call as this. This independence is lost because there is a dependence here. Okay, yi minus y hat is equal to 0. This is some kind of a dependence part. So that we have to take care. Another is this xi ei. That is also equal to 0. No more other constants. So these dependent parts has to be subtracted from the degrees of freedom. So if you look at the concept of degrees of freedom, you have to subtract the constraints from the actual number of independent parameters. Okay. Yeah. So yeah. So this ms residual is now ss residual by n minus 2. Fine. Uh, okay. Why we have divided it with n minus 2? This ms residual. This is because if you just look at this SS residual upon n minus 2, this will come up to be sigma square. And we generally define this term as the MS residual. So what is the importance of this? The importance of this is that this now is one of the unbiased estimator for the variance, the population variance. Sigma square is the population variance, but sigma square is unknown. So we need from the sample something which is close to the variance. And we found that this SS residual by n minus 2 is actually equal to sigma square. You can derive it. The derivation is already given in the week 1 lecture. You can refer to it. Okay. I'm not deriving it, just I'm trying to apply this concept. Okay. Unbiased estimator for population variance. That's why this MS residual we generally write as SS residual by n minus 2. If it is still not clear, let me also show you this. Then it will be much more clear. See this. This is yi minus yi hat square. This I have already told you. SS residual, right? Now, if you divide it by the number of independent number of samples, then what will happen? This is nothing but the mean square, right? This is the square and then taking its mean. So it's the mean square. Mean square, some kind of a variance because this is the some kind of a variance. This is showing some kind of a variance. Instead of y bar, you are writing y hat, right? So that's why this is one of the estimators for variance. Okay, so that's why this is called the MS residual. That is because of the residual, SS residual. It is coming this residual, and this is a mean square term. So this is a mean square term, right? You can see it from here. Now, is it clear or something? Okay. Fine. Now, let us come back to the hypothesis testing part. You can also visit my last notes or and lecture. There I have a little bit talked about the estimators. You can check that and then try to see that, right? So that will be helpful. Yeah. Now, what do I have written? So this is beta 1 hat minus beta 1 divided by root over ms residual by s. Okay. So at h naught, it is actually equal to t n minus 2 alpha by 2. Now, just I am writing it arbitrarily, but let me show you. See, here we have come up to this part, right? Beta cap minus beta divided by root over sigma square sxs is n01. Problem is that this sigma square is unknown, but we have an estimator for sigma square, which is ms residual. So we directly write here, instead of sigma square, we directly write here ms residual root over that. So this is already we can write. But when I write this, when I write this instead of sigma square by sxx, if I write this, this no longer becomes, it is not related to normal 0, 1. It becomes t n minus 2 alpha by 2 distribution. That is t statistic distribution. Okay. Now again, you have to refer to my last class where I have shown that how this, if I put this ms residual, then how it is going to be t distribution instead of n01 distribution. Okay. So this you have to look it from there. Fine. So this is nothing but the t distribution. So now let us calculate the t statistic. So for t statistic, t we will use this condition of H naught. So we will assume that H naught is true. This is the steps of testing the hypothesis. So this is beta 1 hat minus beta 1, whatever is written, just let me write it once again. MS residual divided by SXX at H naught is true. What is H naught? Beta 1 is equal to 0. Put beta 1 equal to 0. So what it happens? So it will be beta 1 hat divided by root over MS residual divided by SXX. Right? So this becomes my key statistic. Okay. I know beta 1 hat value. We have calculated how much it is 12.21. Now, SS residual, SS residual is SYY. This is also from the lecture notes. You can check it. Beta 1 hat SXX. This we can calculate easily. Okay. So SXX is 154. SYY, what is actually this? This is nothing but summation xi minus x bar whole square. Okay. Similarly, SYY is summation yi minus y bar whole square. Okay. And let us say SYY is what we have to calculate. So do we have yi minus y bar? Yes, we have this. Okay. So this we have to square. So let me just write it here. What we need to square. So this will be 180 with a minus sign square plus minus 38 whole square plus 22 whole square plus 52 whole square plus 82 whole square. That comes out to be, I have calculated, it is 25280. Okay, so this becomes my SYY. Nothing but this. Okay, this we have calculated. Uh, which one? Just can you repeat? Yes. Mm, yeah, square, like this one. Right? Xi minus x bar whole square. Huh. Right. Okay. Yeah, you can use it. Here, actually, I'm following what Sir has written, so I am just following that. Okay. So you can follow your own. That's okay. Because ultimately, it will come out to be this, right? Xi minus x bar whole square. So, summation. Yeah. You can use it. Absolutely. It's all your freedom. You can use it. Anything you want. Fine. So this is the SYY. Okay. So now finally SS residual is, because ultimately our aim is to find out MS residual. Right. This is my aim. And MS residual we know is SS residual by n minus 2. This is known. So how to find out SS residual? So SS residual is, I have already written this. So let us just put the values. So it is 25280 minus 12.21 into 154, right? And if I have calculated 233,99.60. This is the SS residual which we are getting. Okay, just following this. Now we need to find MS residual. Let's see what is MS residual. So this becomes SS residual divided by n minus 2, which is nothing but SS residual we have calculated. So let me write here 23399.66 divided by 5 minus 2, right? So finally, I'm getting this as 7799.8. Okay, this point. So this is my MS residual. I have calculated my MS residual. Correct? SXX, I know. So what else we need? Beta cat root over MS residual divided by SX. Okay. This known, this is known, this is known. Let us calculate now the t statistic then. This is 12.21, right? Divided by root over ms residual is 7799.8 divided by sxx is 154. Correct. So this t statistic therefore is 12.21. Again I'm writing divided by, if you do this, it comes out to 50.61. How much it is? Root and all. If you do, it will be 12.21 divided by 7.12. It comes out to be about 1.714. This is my t statistic. Okay. This. Fine. Now what we need to test with? We need to test it with t of n minus 2 into alpha by 2. I have said 5% significance level and it's a both sided test. So it will be t 5 minus 2 is 3 and alpha by 2 is 0.05 by 2. So it is t3.025. This, against this we have to test. So what is that? So you have your, okay, this is your t distribution, and suppose this is your 0.025. This is your 0.025 value. Okay. So T3 of 3 comma 0.025, actually it comes out to be about 3.182. So this value is T3 comma 0.025, which is 3.182. What my test statistic comes is 1.714, which is somewhere here, means less than this. Okay. So once we see that t is less than t of 3 comma 0.025, so then what we can say, that h naught has to be accepted. Okay. So h naught, which is what, beta 1 is equal to 0, has to be accepted. So what does that mean? Whatever beta 1 hat we have calculated is not significantly different from 0. Had it been that h naught is not accepted when t is greater than this value, if t is greater than this value 3.182, then we will say that yes, the beta 1 hat which we have calculated is significantly different from the 0 value. Okay, beta 1 is equal to 0 value. So this is the kind of hypothesis testing which we use in the regression. Yeah, tell me. Right. Let me see. SS residual, you can either use this formula, or SS residual can be calculated as, because what is SS residual? It happens like yi minus yi hat square. Okay, so if you have the yi values, let me just write it down, the yi values, then you can also see that. So this is 40, 120, 180, 210, and 240. Correct. You can calculate y hat based on whatever intercept and slope we have got. Beta 1 hat into xi. Okay, so xi also I have to write. So this is the same question. Okay, 5, 7, 12, 16, and 20. So what will you do? Just you will put, you know, beta naught hat, beta 1 hat, right? So the first one will be what? 11.48 plus 12.21 into 5. Similarly, 11.48 plus 12.21 into 7. Similarly, you go on doing it. Finally, whatever the result will come here, okay, yi, that is 40 minus this yi or y1 hat. Okay, this is y2 hat. Suppose whatever value it comes. Okay, so you have to do this yi minus yi hat. So it will be 40 minus y1 hat, then 120 minus y2 hat, so on. You have to go ahead with this, okay? And then sum all these values, square and sum, okay? So yi minus yi hat, you have to square and sum, okay. Right? Okay. This is how you can calculate. Another way is best is to do this. If you know that how it comes, syy minus beta 1 hat sxx, then you can just plug in the value of this and this and get the result. SS residual. Same thing. If you derive, it will come out to be like this. Okay. Yeah. Yes. Yes. Okay. See, I have to then derive this part because just a minute. Actually, it comes. If you look at what you call as your the lecture, if you look at, it is completely derived. Okay, there you have derived, but I have to look into it once more. Uh-huh. Okay, yeah. So, oh, yeah. I mean this one, right? Okay, okay. I just okay. I see. So this is the this is SYY minus beta 1 hat SXX is actually SS residual. You can derive it. Okay. Now this SXX is nothing but this summation xi minus x bar whole square, which is already known to me. And SYY is this yi minus y bar whole square. Now you just square each and every part here, whatever is written. Uh, where is it? Yes. So this is yi minus y bar, right? So you have to square each and individual term and sum it. That is what I have done. Yes. Yes. 12.21. Yes. Into 154 because SX6 is also there. Yeah. Yeah. Right. 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 Oh, okay. Okay. I thought of derivation that you want. Hmm. Yeah. Okay. Okay. So I have missed one step. This, yeah. This is SYY, which we have calculated. Beta 1 hat also we have calculated. And SXX also we have calculated. Okay. So that's why. Okay. Yeah. Okay. Now, next, let us test the hypothesis for beta naught also, because beta naught also has some hypothesis testing thing. Okay, so let's do one. This is the third one. Let's test the hypothesis for beta naught. Hypothesis, same at 5% significant level. So my null hypothesis will be, see, it can be beta naught, can be anything, but I'm writing for this particular case, I'm writing it as 0. Okay. And h1 is beta naught is not equal to 0. It can be any value, so you just have to put it. That's all. When you are applying the null hypothesis condition, you just have to put beta naught. Fine. So to do that, again, we have beta naught capped as, again, this is also a normal distribution of beta naught and sigma square 1 upon n plus x bar square upon s x. This is the variance of the this beta naught hat. If you do the variance, you calculate, then it comes out to be this. So it's a normal distribution. Again, in the same way, if you linearize this, so beta naught hat minus beta naught divided by root over sigma square 1 upon n plus x bar square divided by sxx. Correct. So this is again normal 0, 1 distribution. Fine. Now we will again the same problem arises that sigma square is unknown. Population variance is unknown. So again, we will replace the same because we already have seen that E of M is residual is nothing but sigma square. So just replace sigma square with ms residual. Okay, so it is becoming 1 by n plus x bar square by sx. Again, you can prove that this is nothing but the t distribution with n minus 2 degrees of freedom. This you can prove, and I have already proved it. Last lecture notes you can refer. Okay, so this I have already proved. Similarly, now ms residual is already been calculated to me. N I know, x bar square I can calculate, sxx is known. Okay, for the t statistic, we have to use the same condition but at null hypothesis. So ms residual 1 upon L plus x bar square divided by sxx at h naught. What is h naught? Beta naught equals 0, which I have taken. So I eliminate the beta naught at the numerator, therefore, so I have beta naught hat divided by root over ms residual 1 upon n plus x bar square divided by sx. Everything is known here. It's mostly done. We have calculated ms residual as how much? I have written it somewhere. Yeah, 7799.8. We have calculated it. Okay. N is 5. I know. Yeah. Tell me. Okay. Fine. So x bar, I have calculated how much it is. 12 by the way. So x bar square will be or 144. Correct. And a6x is 154. That is also calculated. Beta naught have also done. Estimated intercept, we have already calculated how much it is 11.48. Correct. Now T is 11.48 divided by root over. What is ms residual then? That is 7799.8, 1 upon 5. X bar square is 144 divided by 154. Okay. So if you now calculate all these things, it will come out to be about very small value 0.122. Again, we are comparing it with the same Tn minus 2 alpha by 2. Alpha is 5%. So it becomes T3, comma 0.025 because it's a both sided thing. Correct. And this I have found already told you that is 3.184. And here also T is less than 3.184. Again, if it is less, that means H naught area. So H naught is sorry, H naught, that is null hypothesis, is accepted. That is, whatever beta naught hat we have is not significantly different from zero. The beta not equal to zero. Okay, so again, if I have to draw it, just look it once again. So this is your t distribution, symmetric distribution. T is the symmetric distribution. This is T3.025. Again, this will be T minus T3, comma 0.025 because it's a both sided thing. So this is 0.025, the area under the curve. This is also 0.025. So area under the curve actually represents the probability. Okay, because this is the PDF, this is the probability distribution or density function. Okay, this entire area is H naught area, and this, if the t statistic exceeds this value and comes over here or here, then we accept the null hypothesis. So these are the H1 area. Fine. So since here the t is coming out to be about some 0.122, which is very smaller than this, so we have to accept the H naught. Okay, that is beta naught is equal to 0. Fine. Now, once we have tested the beta 1 hat and beta naught hat, this hypothesis testing is already been done. Now, we start with the uh, ANOVA table concept and let us see. Okay, so Let's change the color. So now we will talk about ANOVA table. What is that ANOVA? And we will write the ANOVA table for yeah. This is actually analysis of the variance. This ANOVA table, right? Analysis of variance. So in general, if you look at the total variance of the data, whatever the data which I have given or anyone, wherever you find some samples, the total variance of the data is I is equal to 1 to n yi minus y bar whole square. Right. Of course, generally for calculating variance, we divide it with n or whatever the number of samples which you have, you divide. But here I'm just writing the sum, okay, sum of the variability. Fine. So this is what you have. Now, actually through ANOVA table, what we try to do is that we need to understand, so I'm just writing it, need to understand that how much of the total variation, how much of the total variation which I have written above, total variation of the data is explained by the regression model. Because whatever regression model which we have developed is nothing but one of the predictions. Okay, it is not exact. So, how much variation to that of the total variation is mostly uh, observed. So, that is what our main idea is. So, to start with, it's nothing but I have starting with this y minus y hat arbitrarily starting. This is nothing but the residual. Okay, can be written as yi minus y bar plus y bar minus yi hat can be written. It's absolutely fine, I think. So yi minus y bar and just take a summation, the negative outside, and it's yi hat minus y bar. Yi minus yi hat. Finally, so you can see that this is nothing but the deviation of some ith observation because yi is the observation from ith regression model value or predicted value. Okay, this is deviation of ith observation from mean value, and the last is deviation of ith predicted value, the model value. Okay, predicted value from the mean value, right? So it's easy to interpret. Now I will show everything. So let us just draw a graph. This is just one of the conditions. It can be different for different. So let this be x and let this be y. Okay, and let us consider that this is some kind of a fitted line. Okay, and let us consider a point on the fitted line having x something I, and this is yi. This is the y hat because it is a predicted line. So y hat is beta naught hat plus beta 1 hat. This is the predicted line. Okay. Now let us consider that at xi the observation is somewhere here. Okay. Same xi observation is somewhere here. It can be below also. It's fine. So it's y. Okay. At xi this is the observation. And let us consider that the mean value lies somewhere here. All the data sets which you have, the mean value is this y bar. Okay. So therefore, This yi minus y bar, this one, this entire, that is the actual value. Huh? Is it visible now? My screen is not visible. Um, okay, let me go. I can share it. I think some network issues. See, now it is visible. Hello. Whiteboard is not visible. Can you just go out and join again? I think some network issue somewhere because I am able to see one of my screens. Just try that. I am waiting to do it quickly. Yeah. Yeah. Can you just check? Right. Okay. Let me continue from here. So what I was talking about is that this yi minus y bar. This is yi minus y bar. If you square it, it will tell you about the this quantity. That this is actually this quantity. Deviation of the eye of observation from the mean value. The total variance it will give. Now, if you look at this small thing, this is nothing but we have already discussed. This is nothing but the residual, the error. Okay, this is the residual. However, this part is the regression part. This is the regression part because this is the fitted value subtracting or the difference between the fitted value to that of the mean value. This is related to the regression. Now, what we do next is we have to square it. Okay, sum and square. So just the above equation, what I have written here, this one, I will square it and sum it both sides. So just yi minus y bar whole square is summation yi minus yi hat whole square plus yi hat minus y bar whole square. Right. So this is what we do. And this comes out to be the total sum of square. Total sum of square. Okay. This one is very known to us. This is the residual sum of square. What we call as SS residual. Okay. Residual sum of square. This is familiar. Okay. And the last one is called the regressed sum of square. SS regression. I will write regressed sum of square. So finally, we can write this as SST, the total sum of square, SS residual, that is residual sum of square, plus SS regression. Okay. And generally, we calculate the degrees of freedom. Again, if you look at here, this is I going from all going from 1 to n, every summation. So must be n degrees of freedom because n different samples. But we have to remember a constant is there, that is yi minus y bar. The summation of all the anomalies has to be 0. So because of this one constant which we develop, we have to take care of it. So the degrees of freedom of SSP is actually n minus 1. Therefore, SS residual we have already seen, discussed, is n minus 2. And degrees of freedom, if you add it, you will get the degree of freedom of the SS deviation, which is nothing but 1. Okay. So now, what I will do is that, fine. So now, we have already talked about SS residual so many times. So SS residual is summation yi minus yi Yes. This is the total sum of square. The total. T for the total sum. Yeah, this yi minus y1 whole square, the total variance. Okay. Yeah. So this is nothing but summation ei square, as you know. Okay. And we have shown that ei square by sigma square, not in this class, earlier class. This is nothing but chi square in minus 2 distribution. It is the chi square distribution. Or you can say this chi square distribution is nothing but normal 0, 1 whole square distribution. Okay. This actually leads to chi square element. So again, sometimes I think some network connection issue. I don't know. But here I am seeing it. Okay. Uh, it's okay. It's fine. Now it's visible, right? Okay, I will continue. So next is SS regression. Let us talk about this somewhat what we can see from here. So this is actually what is that? So yi hat minus y bar also. This is SS regression. So this is summation. Yi hat is nothing but we have seen beta naught hat plus beta 1 hat xi, correct? Minus this y bar is nothing but beta naught hat minus beta 1 hat x bar, this square. So this beta naught can be cancelled. I have now beta 1 hat and xi minus x bar, this entire square. So what we get is beta 1 square, beta 1 hat square, and summation of xi minus x bar whole square. And I have told you that this is nothing but s x. Okay, so SS regression is this. Okay. So this is one of the things I've shown. And now let us write the ANOVA table, how we write it. Okay. So in the ANOVA table, first we write the source of variation. Source of variation. We write the degrees of freedom. We write the SS, the sum of squares. Then we calculate the MS, the mean sum of squares. And finally, some distribution called the F distribution, which we will come. Okay. So first thing is regression. Next is residual. And the final is the total. We have seen this is the one of the things is the regression, another is the residual, and the total. And we have seen that this is degree of freedom is 1. For the residual, it is n minus 2. For total, it's n minus 1. For regression is SS regression. SS regression we have calculated. SS residual also we know. And this is SST, the SS total. Fine. Now, what is MS regression? MS regression is nothing but SS regression divided by 1. Degree of freedom. Just you have to divide it by the degree of freedom. MS residual is SS residual divided by n minus 2. Okay. Now, let us see one thing. Yeah. We know that this n minus 2 MS residual divided by sigma square is generally chi-square n minus 2 distribution. Okay. From the previous lectures and classes. Okay. This we know. Also, I am writing this MS regression by sigma square is actually chi-square 1 distribution. Now, why is it coming? Why is it chi-square 1? Is because you cannot just write this as chi-square 1 every time. So, it actually starts from the fact that I know that MS regression is nothing but SS regression, okay, divided by 1. So, SS regression only. So, which is beta 1 hat square SX. This we know. Also, we know that beta 1 hat is normal beta 1 sigma square by Sx. Correct? So, while doing the hypothesis testing, we know that beta 1 hat minus beta 1 root over sigma square by Sx is nothing but normal 0, 1. And I will just write this sigma square as ms residual divided by Sx, which is nothing but the what do you call it, the t distribution. But the problem is that now this, if you write, or just a minute, not this. Let me. I have gone one step ahead here. Okay. Let us just fix it here. Apply the condition of H naught. What is that? Beta 1 is equal to 0. If beta 1 is equal to 0, then what it becomes? Beta 1 hat divided by root over sigma square by Sxx. Right? This is normal 0 1. I know that square of normal 0 1 is chi square 1. So I square both sides. So becomes beta 1 hat square divided by sigma square into Sx. This becomes chi-square 1. Why? Because normal 0 1 whole square is chi-square 1 distribution. What is this? I know this is ms regression divided by sigma square. That's why it is called the chi-square 1 distribution. We can, so this is how we can show. Okay. Finally, what the f I was talking about, this f distribution is nothing but f is actually ms regression divided by ms residual. Okay, and this is actually f of n1 n2 sorry n2 comma alpha. Okay, so this n1 in this case is 1 because regression has 1 degree of freedom, n2 residual n minus 2 degrees of freedom, and alpha is the that your what you call as the probability, that is the significance level. Okay, so in general, the definition of Fmn is nothing but x by n divided by y by n, where m and n are the degrees of freedom of x and y respectively, and x and y are two distributions, independent distributions. Okay, so now let me just put another thing, that let us write the ANOVA table for our uh, the data which we have. Okay, so this is the fourth problem. Write ANOVA table. Write ANOVA table and test using this, and test the hypothesis of beta, hypothesis of beta 1 using this X distribution. So actually F and E are related. So that's why either or. You can do it with T distribution, you can do it with F distribution, anything. Okay. So again, so we can write that ANOVA table, source of variation. Okay, degrees of freedom. This is SS, this is MS, and finally A. Okay, so this is the regression. I'm writing short form now. Residual and total. Degrees of freedom we already calculated. This is n minus 2. So in our case it is 5, right? So 5 minus 2 is 3. This is 4. 3 plus 1 is 4. This SS residual, we have all, sorry, this is regression now. How we can calculate SS regression? We have already have one formula, that SS regression is nothing but beta 1 hat square Sx. So it is 12.21 calculated already. Sx 154. How much it is? 22958.95. So it is 22958.95. Right? We have calculated SS residual, that is 23399.6. And what about SS total? SS total also we have, this is yi minus y bar whole square summation. That is nothing but SYY. So this is 25280. Now MS, how will you calculate? This will be same, right? This is regression by 1. Okay, so uh, this is actually 22958.95 only because by 1 it is. This is, we have calculated MS residual 7799.8, just divided by 3. So ms regression I have found out, ms residual I have found out. So f you can find now. So f is what? ms regression divided by ms residual. How much it is? So it comes out to be about 2.94. Okay. So now again to test h naught, same beta 1 equal to 0, h1 beta 1 not equal to 0, same 0.05 or 5% significance. You will find f of 0.05, 1 comma 3. Why? ms regression has 1, ms residual has 3 degrees of freedom. So that comes out to be 10.13. You have to check the f 0.05 1 comma 3. Okay. So that table, if you check, it comes out to be 10.13. However, if statistic comes out to be 2.94. So 2.94 is much less than 10.13. That suggests that again each knot is accepted. If it is greater, then we could have rejected and accepted the alternative hypothesis. Okay. So it is actually the same. So we can prove that f is actually equal to t square. The t statistic which we have done, its square is nothing but f distribution. Okay, so how we can prove? Just one liner. T we have written beta 1 hat ms residual divided by sx, right? So just do t square. So what is that? Beta 1 square divided by ms residual sx. So what is that? Beta 1 square sx is ms regression divided by ms residual. Actually, this is it. So beta 1 square SXS is actually SS regression, but MS regression is nothing but SS regression by 1. So it's same. Okay. So T square or F, they are related. So you can do it using T distribution test or you can do it using F distribution test. Okay. So this thing is done. Next is very important concept, coefficient of determination. These are quick concepts. Just I will write and finish it. Because yeah, coefficient of determination. I think confidence interval is also there, so we will do that and finish it today. Okay. So next concept is the coefficient of determination. Coefficient of determination. So how we can define that is actually r square. We define it like this: is SS regression divided by SS total. That is, out of the total variability in the data, how much percentage of the total variance is explained by the regression model. That is what is the main definition of this. So it's a fraction. This is the fraction of total variability explained by regression model. Okay, this is how it can define. Also, you know that SS regression can be written as what? SS T minus SS residual divided by SST. This also is one of the definitions. It becomes 1 minus SS residual divided by SST. So if you don't want to calculate SS regression, you know SS residual. We calculate generally SS residual and SST also if you can calculate, then we can also calculate this coefficient of determination R square. Meaning is simple. Like this is suppose your x and y axis, and this is your fitted line. And let us say that all the points are on the line. Then all the regression model is actually explaining well the entire data set. So your R square is actually equal to 1. 100% of the variability is explained, of the total variability is explained. However, if you have some data which is somewhat scattered, here, somewhere, and you are drawing a line like this, you may get it to be about some 0.6. Nobody knows. I'm just writing arbitrarily. Okay, so you can get less than 1. So that means what? 0.6 means what? 60% of the total variability of the data is explained by the regression model. Variability is explained by the regression model. Okay, so this is the thing. When this SS residual is equal to 1, sorry, 0, suppose 0, okay, then what will be the answer? Answer will be 1. What does that mean? That means there is no error at all. Okay, this case, no error, nothing is there, no deviation from the y hat. So that is one of the thing. So again, since we are doing applying every concept into the same problem which I have first given, so let us find the fifth is that find the coefficient of determination of whatever the data which we have. So let's see whether whatever model which we have generated, the estimated model, is it really capturing good variance of the total data or not? Let's see. So how will you do it? Okay, you have R square is equal SS regression divided by SS. See, SS regression we have calculated 22958.95 divided by SST is 25280. Correct? Which is SSY only, right? So this comes out to be about 0.0909. So about 91% of the variability is explained by the regression model. It's quite good. Okay. So 91% of the total variability is being explained by the regression model which we have estimated with the beta 1 hat and beta naught hat, slope and intercept. Fine. So this completes the coefficient of the determination, the concept of coefficient of determination. Let's quickly go to different concepts. Yeah, half an hour is there, so we can do it. So now, yeah, the next is confidence interval for beta 1. See, finally, what happens is that when you have sample, we have estimated the estimator of the slope, beta 1 hat. Can we give an estimate using that beta 1 hat that the actual population parameter beta 1, where what is the interval, means where this beta 1 can lie? So this is the confidence interval of the slope, beta 1, the population parameter. Always remember, confidence interval is for the population parameter using the estimator. So beta 1 hat is my estimator of slope. I want to see that using this beta 1 hat which we have calculated, can we give an interval where beta 1 will lie? Okay. These A and B values can we give where this actual population parameter beta 1, the actual slope of the population, will lie. So that is what is the question that we pose. So obviously, y was what? The regression model beta naught plus beta 1x plus epsilon. This is what your uh, actual simple linear regression model, the population model. And estimator of beta 1, estimator of beta 1 is nothing but beta 1 hat, which is nothing but Sxy divided by Sxx. Same with that definition. Same definition. Okay? Sxy is given by this and Sxx is this. Just define it. You can define it in any symbol. It's absolutely your choice. Also, we have seen that E of expectation value of beta 1 hat is actually equal to beta 1, which is an unbiased estimator. Okay, and also variance of beta 1 hat is sigma square upon S This we have already seen. And we know that B1 hat, beta 1 hat is normal of the, the expected value of beta 1 hat, which is beta 1, comma, variance. So sigma square by S. This is the normal distribution. No, writing this beta 1 hat in some linear uh, random variable, so becomes this sigma square by S x. This can be written as normal 0, 1. Okay. And again, most of the cases and whatever question which I have also posed, I have not known the sigma square. So this is unknown. And one of the most popular estimator for sigma square is K's residual. This is an unbiased estimator for the variance. Okay. So we will use that. So what is that? Beta 1 hat minus beta 1 divided by root over, we replace this with Ms residual by Sx. Now, by chance, in the question, if they provide you the sigma square, don't use this. Use this one, okay? And use the normal 0, 1 table, normal table. Not don't use this T distribution table. T distribution only when the sigma square is not given in the question. If it is given, sometimes by some trick they may mention the sigma square. Just use normal 0, 1, okay? So yeah, so this becomes T n minus 2 alpha by 2. It's a both side distribution we have talked about. Okay, so this is what it is. I've already shown it. So this is the alpha by 2, and this is minus T n minus 2 alpha by 2. This is plus T n minus 2 alpha by 2. Right. So this is one statistic. Okay. And since it is both sides, you can take a mod and all these things. Okay. So now what we do here is that one of the thing is that this beta 1, okay, this beta 1, uh, we can write that is less than equal to beta 1 hat plus t alpha by 2 n minus 2 root over ms residual divided by s. This is one of the things, because as you can see, means it can be on the both the sides, because it will be either plus or minus. Okay. Interval is in between these two. Okay. So there is a plus sign, plus, and there is a minus. In between, the beta 1 will lie. Again, beta 1 is actually greater than equal to beta 1 hat minus t alpha by 2 n minus 2 root over ms residual divided by s. Okay. So finally, the confidence interval. Which confidence interval? Alpha by 2 based on alpha confidence interval. Alpha percent confidence, actually 1 minus alpha percent confidence interval is this. So I will tell you what is it. So if you look at, let me make a big box here for me. So this is the probability. What you will find is that the probability of beta 1 hat minus t alpha by 2 n minus 2 root over ns residual divided by s x beta 1 beta 1 hat plus t alpha by 2 n minus 2 into, okay, this is in multiplication, ns residual divided by s x. This probability is actually equal to 1 minus alpha. So if you have say 5%, then this probability will be 95%. So it is a 95% confidence interval. Or yeah, so it's okay. Okay, so this is the 95% confidence interval for beta 1. So what is the confidence interval is this and this. So beta 1 hat minus t alpha by 2 n minus 2 root over ms residual divided by sx comma beta 1 hat plus t n minus 2 alpha by 2 root over ms residual divided by sx. So This is the confidence interval. And so in the question, let us, the sixth problem is that the question which I have posed, there you find the confidence interval, 95% confidence interval for beta 1. Okay, so let us do it. First, we need to find out this thing. Okay, t alpha by 2 n minus 2. So this alpha is then what? So it will be 0.05 because it is 95%. So it comes out to be 0.95. 1 minus 0.95 is the significance. So becomes 0.05. So this by 2 comma n minus 2. So that means t of 0.025 divided by n minus 2. 5 minus 2. So t of 0.025 comma 3. And we have actually estimated this. This is about 3.18. Okay. So this t we have already found based on 95% confidence interval. Okay. Now, okay, we know beta 1 hat, which is 12.21. We have already calculated it. MS residual is also known. How much it is? It was, I think, 7799.8, something like this. Check. Yeah, 7799.8. SXM 150. If you calculate this MS residual divided by SXM, that comes out to be 7799.8 divided by 150. How much it is? About root over, I think, 50 something, 50.65 comes out to be 7.1. Okay. Now just putting the values. So lower bound, lower bound will be always subtracting from the beta 1 hat. So it will be beta 1 hat minus t n minus 2 alpha by 2 root over ms residual divided by s. Don't confuse between this n minus 2 and alpha by 2. I am sometimes writing alpha by 2 comma n minus 2. Same thing. Okay, just writing notation. 12.21 minus 3.182 root over what is ms residual is okay. This already we have calculated. So this is this root and entire thing is 7.1. So it comes out to be uh, check. Yeah, it's minus 10.44. This is the lower bound. Okay. What about the upper bound? Just plus. It's easy to calculate. So it's beta 1 and plus tn minus 2 alpha by 2 root over ms residual divided by s. So what is beta 1 and? Is 12.21 plus 3.182 into 7.1. Okay. So it will come out to be about 34.86. Okay. So the confidence interval is minus 10.44 to 34.86. This is the confidence interval for beta 1, the actual population parameter. And what we have got as the estimated, we have got 12.21. So 12.21 lies in this interval. So this is one of the confirmation that this 12.21 beta 1 hat, what we have estimated, is actually lying in the confidence interval of the this beta 1, the actual population parameter. So that is the validation. Fine. So this is the estimation of beta 1. Okay, next one. Uh, we have interval estimation for the mean response. That is the expected value of 1. We will see that. And yes, so that's all. I think we have two concepts left and about 15-20 minutes. So we can easily do it and finish. Okay. So these are all the problems which can come, right? We have only one question which I have in the beginning started, and different problems, whatever we are learning from there, we are just applying it. Okay. So next is the interval estimation of the mean response. Interval estimation of mean response. Okay. So what is that? What do you mean by mean response? Is nothing but the expected value of y. You know that when you have y set of data, expected value is nothing but the mean of the distribution. Okay. So E of y is the mean response. So interval estimation of, see, it has to be for one particular value. Okay. So we want to do the interval estimation of E of y at x is equal to x naught. Don't confuse it with the conditional probability. This is not the conditional probability. This is y at x is equal to x naught. Okay, not the conditional probability. So what is that? So okay, just let me write. Y at x is equal to x naught will be what? Will be beta naught plus beta 1 x naught. This we know. This can be written. In fact, if you do the expectation value of y at same x is equal to x naught, this is nothing but same thing, beta naught plus beta 1 x naught. Because x naught is a constant, it's a random variable. Beta naught and beta 1 are also constant. So it will remain as it is. Okay. Now, okay, sorry. This will be some epsilon will be there. Sorry. Okay. And we know that if you do E of this epsilon, there is an assumption in the simple linear regression that expected value of the error is 0. So this is gone. So it will be only this. Okay. Also, E cap, the unbiased estimator of this. So y at x is equal to x naught is nothing but beta naught hat plus beta 1 hat x naught. Right? So this is nothing. I think I have just. So actually it has to be y hat, right? Y hat, its expectation value. That is nothing but we are calling it E hat. Okay? Because y hat is nothing but beta naught hat plus beta 1 hat x naught because x is equal to x naught. So this is the unbiased estimator. Okay, fine. Now next is that variance of, let us see the variance of beta naught hat plus beta 1 hat x naught, okay, which is nothing but y hat. This is nothing but variance of y hat. Y hat can be written at x is equal to x naught. Just remember this. All we are doing at x is equal to x naught. So what we can write? Variance of, see, this beta naught hat can be written as y bar minus beta 1 hat x bar, okay, plus beta 1 hat x naught. How? How we can write? We know that beta naught hat is nothing but y bar minus beta 1 hat x bar. We have calculated the estimated intercept with using this. So from here, just I'm replacing beta naught with this. So variance of, finally, y bar minus beta 1 hat x bar minus x naught can be taken as. So there are two variables, variance of A plus B. If you do, then it becomes variance of y bar plus variance of minus beta 1 hat x bar minus x naught. I've taken the minus inside plus two covariance of y bar and this minus beta 1 bar at x bar minus x. Okay. This covariance generally is equal to 0. Okay, this happens to be 0. We have to see it, but I am not proving it right now. You can check the lectures. So variance of y bar. See, y has different samples: y1, y2, y3, so on. Okay, using central limit theorem, because each of them has identical and independent distribution. Y1 is having an identical distribution as y2 and y3 and y4, like that, but they are all independent. When you have this, if you sum this yi divide it with n, it becomes a normal distribution. This is using central limit theorem. Okay, so variance of y bar is if variance of y is sigma square, then variance of y bar is sigma square by n. Okay, it happens. With central limit theorem, it comes. What about this? Variance of some constant. This is constant x bar minus x naught. So I can write x bar minus x naught whole square. If you take the minus also, it will be plus. Okay, and variance of beta 1. Okay, because this is a constant, so you can just take it out. So becomes sigma square by n plus x bar minus x naught whole square. Variance of beta is, we have seen, this is sigma square by sx. So finally, variance of y hat at x is equal to x naught is sigma square 1 upon n plus x bar minus x naught whole square, sigma square, let me write it. Sigma square 1 upon n plus x bar minus x naught whole square divided by sx. Quite similar to that of the beta naught hat variance, where you have written x bar whole square divided by sx. That's all. Okay, so we know now the variance of y hat. We also know the expectation value of y hat, which we denote it as e hat. Okay, now we need to see. So I can write e hat, which is nothing but e of y hat at x is equal to x naught is nothing but, because e hat is nothing but normal distribution with beta naught hat plus beta 1 hat x naught, comma, this variance which we have got 1 by n plus x bar minus x naught whole square by s. Okay, so this is the normal distribution. Same way, we will just come to a statistic. So how will you do? So this is e hat minus e, same as what we have done earlier. Instead of beta 1 or beta naught, we are writing expected value of the y at some position x naught divided by root over sigma square by, no, not sigma square by, it's 1 by n, the variance, that's all. X bar minus x naught whole square by sxx, right? This is what you get, and this is nothing but normal zero. Again, similarly, if you put this sigma square, replace it with ms residual, because sigma square is unknown. The same way, we have minus e divided by, you have ms residual 1 by n plus x bar minus x naught whole square divided by x. Okay, this will be at h is equal to h naught is actually tn minus 2 alpha by 2. The same. Okay, so I'm just not just proving all those things. You can check the lecture notes, but this is the, so I just write the confidence interval directly. So this is the confidence interval e hat minus t alpha by 2 n minus 2 root over ms residual 1 upon n plus x bar minus x naught whole square by sx. This is the lower bound. Upper bound is e hat plus t alpha by 2 n minus 2 root over same thing ms residual and 1 by n plus x bar minus x naught whole square divided by x. Right? So this is your confidence interval. This is the upper bound, and this is lower bound. Okay, so this is your confidence interval. Again, for 95% confidence interval, if you want, then you have to put alpha by 2 to be 0.025. Because this probability is, if you look the probability, that becomes 95%. Okay, so based on that significance, you have to just calculate. So it's just 1 minus alpha. I have shown it in the last question. Okay, so we will do one problem here based on this, and after that, one more thing is there, but just I will write that and end the session. Okay, because yeah, so this is I think the seventh or eighth, I don't remember. So estimate the interval for mean response. That is P of y, the expected value of y, when at one point, always it will be at one point. So it's equal to 12, let's say, at 0.05 significant level, or sometimes you can say that 95% confidence interval. Both are same thing. Okay. So again, what is E hat therefore? E hat is beta naught hat, we have calculated, beta 1 hat, it's not. So that's just calculated. I know this is 11.48, this is 12.21, and x naught is 12. Comes out to 150. Okay. We also know that t of 3, comma 0.025, because it is a 0.05, we have to do alpha by 2, 0.025. And this has to be always n minus 2. So 5 minus 3, this is 3.18. Done. Next is you have MS residual, which is 7799.8, N5, SXF 154. What else? X bar 12, we have already calculated. X naught is also 12. That's why I've chosen 12, so that one of the terms becomes 0. So MS residual, what is that term? MS residual, this one. So MS residual, let us calculate this. 1 by n plus x bar minus x naught whole square divided by sx. So MS residual is known, so how much it is? 7799.8. 1 by n, 1 by 5. 12 minus 12 whole square divided by 154. Correct? So 7798.99.8 into 1 by 5, because this term is 0, comes out to be 1559.96. But we need to take the root of this. So 1559.96 is 39.49. So this is nothing but this term. Oh, where is it? This one. It's root. Okay, square root. Because in the confidence interval, we need the square root of this. So this. So finally, let us calculate the upper bound. The upper bound is what? So E hat minus T alpha by 2 n minus 2. So I'm writing it to the MS residual 1 by n plus x bar minus x naught whole square divided by x. Okay, so E hat we have calculated to be 158 minus 3.182, and this root we have calculated to be 39.49. That comes out to be 283.6. This is one of the upper bounds. Now, lower bound we have to calculate for the confidence interval. So the lower bound comes out to be E hat plus T alpha by 2 n minus 2 root over same as residual 1 upon n plus x bar minus x naught whole square divided by s x x. That's all. So again, we had I know 158 plus 3.182 into 39.4. So you can see because of the symmetric distribution, same thing is being subtracted and added. So that comes out to be 30, oh, sorry, minus lower bound 32.34. So finally, the 95% confidence interval, 5% significant confidence interval is 32.234, comma 283.6. So this is what your uh, is estimate. Okay, is confidence interval, the actual population. But you know that E hat is 158, which lies in it, which is a validation that it is fine. And of course, it will be doing because we have taken this as the reference 158 years, subtracting sometimes and then adding sometimes. Okay, so we have 9 minutes left. We can just, I am just writing the last part, but I will not solve any question based on that. That is how we can predict a new observation. So that is the last part of the regression model. I'll just write the confidence interval and stop. Okay. So this is the prediction of new observation. Okay. So for x is equal to x naught, whatever data we have, you can take any one x naught. You have a corresponding y is equal to y naught, right? And actual regression model, if you write, it is actual. Okay. Actual LRM, linear regression model, which is beta naught plus beta 1 x naught plus epsilon. So here we are not putting the cap because this is the actual value. We are not, this is the not the expected or the estimated. Okay. So now what happens is that corresponding to y naught, there is a y naught hat. This is the estimated one, which we generally calculate. Estimated y, which is actually beta naught hat plus beta 1 hat x naught. This is your y naught. Okay. So using y naught hat, can we find? So using y naught hat, can we find an interval of some significance, of some alpha significance? Can we find interval of alpha significance for the actual y naught, the new observation? Okay. So this is the prediction of the new observation. So based on if you have your y naught hat, you don't know what is y naught, right? Because this is the population y naught. But we definitely can calculate y naught hat, which we have seen. We can calculate. Okay. So based on this y naught hat, this estimated y, can we calculate an interval for this actual population parameter y naught? That's all. That is the prediction of new observation. So for that, I'm not going into the derivation. We generally get the upper bound in the same way. If you look at the derivation also, it will be the same way, which I have calculated for E cap, beta naught, beta 1, everything, same way. So the upper bound is y naught hat, okay, plus upper bound will be always plus with the y naught hat. Again, Tn minus 2 alpha by 2 root over. There is a difference here. So this is ms residual 1 plus 1 by n plus x bar minus x naught whole square by sxx. Okay. Instead of what I was writing in the expected or the mean response, it was only 1 by n plus this. But here is 1 plus this. Okay. This is the only difference which is there with the e of y and this case. What about the lower bound? Just the same thing, but subtracted from y naught minus pn minus 2 alpha by 2. Same thing, ms residual 1 plus 1 by n plus x bar minus x naught whole square divided by s. Okay, so these are the upper bound and the lower bound. So for again 95% confidence interval, if they ask 95% confidence interval of the new observation y, new observation y at x is equal to x naught, then we can find an estimator, that is y naught, that is beta naught hat plus beta 1 hat x naught. This we can find out based on whatever the estimates we have. This we can calculate. So it will be for our case, it was T3.025. So this is done because 95% means 5% significance, which can be written as 0.025 because it's a symmetric distribution. Once this is done, ns residual you can calculate. We have seen n you know, x bar minus x naught you can calculate. S6 is also known. So everything is known. So upper bound, lower bound can be easily calculated. Let me just check the expression once more with where I have written. Just let me check whether it is fine or not. Once it is done, we can stop. Just a minute. Check once more. The next class we can go with multiple linear regression because I don't find any question in the assignments of the multilinear regression. So we can just leave it for today. Yes, it means minus 2. Right. This is what. Yes. Okay. So this is what we have for today. So that's all. Okay. So I'll stop here. I'll share all these notes. Look at the what you call as the course structure. Not the course structure, but the lecture, because uh, the way it is taught there in the course is very nicely done. And for problem solving, you can refer to this material. And yes, also during problem solving, which are the most important points which I have used, which are the more important expressions which I can use to minimize the time constraints. For example, let me show you one case uh, here. You can save huge amount of time because in the main exam you might have to save time. See, if you calculate this SS residual by actually putting these things like yi hat and all these things, so yi hat calculate and everything, then it will take huge amount of time. Rather, if you use this expression, that will be helpful. Okay, sy1 minus beta1 hat s6 to calculate s6. So these expressions, if you just remember and apply, then you will be easily uh, solving with minimal use of time. Okay, so we have, but what I have covered here is the entire thing, entire concepts, and we have applied that in a particular example like this, which I have put. This is the example. Here I have applied each and everything. Okay, so yeah, that's all. So you will be able to understand which expressions are important to calculate what, like SS residual, which I have shown. So it will be easier for you. How to calculate MS residual and everything, you will be clear with it. Okay, so I will share all these notes as well as recording. Okay, any question from your side, or if it is not there, then we can stop. Any questions?